So, welcome back friends. So, we were dealing with two aspects in the last previous lecture. So, the first one was about what the Dirac theory tells you about. So, how do you test the QED, what the entire process about higher order corrections and how important these higher order corrections are. Okay. In these are virtual corrections, these are virtual, or sometimes they are also called radiative corrections because it comes from the radiative field of the electron of the photon essentially. In those days essentially it was only the radiation corrections which was considered. How do you deal with meaning how do you test that these corrections are there and in an experiment, and how do you know that these corrections can be calculated, okay, and they are precise, essentially the theory is correct. So, this entire theory which we build, that you have relativistic Dirac equation and then you have Green's functions methods which give you Feynman rules, and of course you can do these cross sections, okay, with all the 5 basic cross sections which we have computed and everything, but those are all tree level process, and the cross sections can be prone to experimental error bars which are very large. Okay, experimental large error bars could be large in a cross section computation in a experiment essentially, because they have to be measured in a collider or a small scale accelerator or something like that. Whereas there are some process in which you can really test your theory to the ultimate level, to the maximum level possible essentially. So, that is one of the things which we call is the magnetic moment of the electron. So, the magnetic moment of the electron, as I mentioned that this magnetic moment of the electron is coming from the Dirac theory. As I said, the Dirac theory has is built for spin half particles. We made the connection with Lorentz theories, and so we said that the Lorentz theory tells you that spin half fermions follow the spinors, essentially they form as a representation of Dirac spinors. So, we saw it from that particular viewpoint that the Dirac equation always gives you corresponds to spin half fermions essentially. So, naturally if you look at the gyromagnetic ratio of spin half fermions, it should be 2, it should be exactly 2 essentially. That is a prediction of the Dirac theory. The gyromagnetic, if you put it the Dirac theory in an electromagnetic field, which we have been doing it in the magnetic, which we have been doing it so far. And so, and that means that G minus G of the electron should be equivalent to 2. So, the G of the electron should be equivalent to 2. But then if there are radiative corrections, these radiative corrections or the higher order perturbation theory corrections will move away from G is equal to 2, will move away from G is equal to 2 essentially. So, from G is equal to 2, okay, it will be shifted, by these corrections, each of them giving you a loop factor essentially alpha times some loop factor times some constant essentially. So, what you measure or what you look for is this, the difference between G and 2, the difference between G and 2, which you call it as A. Which you call it as A. So, the A is the difference, that is the difference of the gyromagnetic ratio purely from higher order effects. So, if it is difference from 2, that means you are calculating these corrections purely from higher order corrections. So, from virtual corrections, and that is you can calculate using your renormalizable theory at any order in perturbation theory, because the theory of QED is renormalizable at all orders in perturbation theory. So, you can calculate this in any order perturbation theory, and then you do the same thing in an experiment, and this experiment essentially gives you the corrections and does this calculation at a very highly precision essentially, and that these calculations are not easy, and neither the experiment essentially, both of them actually took few decades of work essentially at highest order, and the current level is that G minus 2 theory minus G minus 2 experiment matches of the order of 10 power minus 10, essentially matches of the order of 10 power minus 10, that it is so precise, essentially it is so precise, the theory matches the work which is so precise essentially. Okay. So if the theory matches the work so precise, so that then there is also the other thing, you can also calculate the corrections to the couplings essentially alpha. The alpha you can calculate it in theory, the corrections to alpha, which is theory, and this has some number up to some 10 decimals. Okay. So alpha inverse will be 137 something 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 something, and alpha experiment which is measured from quantum Hall effect essentially matches this up to 10 decimals. Quantum Hall effect. So the theory is very well stable essentially, it is very well calculatable and everything essentially. In the relativistic quantum field theory, or the one which we built in the form of Green's functions, renormalization, cross sections and everything, it works very well. Of course the techniques have to be modified, essentially we are using Green's functions techniques, and from there you get your Feynman diagrams, but how do you solve these Feynman integrals at higher and higher loops is a different technique. It does not matter whether you use quantum field theory or Green's functions to get your Feynman rules essentially. Okay. And then to solve this is a completely different problem. To solve this thing essentially you have to solve several hundreds of diagrams, and when you do this computation which may take several years of work, you see the theory works fantastically well and everything. But the full quantum field theory is required essentially. When we do this we have full quantum field theory required essentially, but there are some things which cannot be exactly addressed in a full quantum field theory, and we have to resort to the hodgepodge thing which we learnt in this course, essentially using part of the non-relativistic part and using techniques from non-relativistic and some parts from relativistic essentially, and these are very important sort of states which we do not understand at all in relativistic sense essentially, which we understand reasonably well in quantum mechanics, but in relativistic quantum mechanics we do not really completely understand them essentially, or we do not have enough techniques to deal with them essentially, we do not have proper. These are called bound states, these are bound states. How do you deal with bound states in a relativistic framework essentially, how do you deal with a bound state? In quantum mechanics bound states are ubiquitous, and you have hydrogen atom, negative energy states and everything. And how do relativistic states appear in bound states appear in quantum mechanics, relativistic quantum mechanics? In a Feynman, I will give you one example in a Feynman diagram language. I gave you last time, this is the same example, that the statement is that the bound states appear as resonances or poles of the S matrix element. They are appearing as the poles or divergences in the S matrix element. Now one way of looking at how these divergences appear is that you have several. So if you take a simple scattering process, you have several soft mediators which are exchanged, and the sum of all these ladder diagrams is a divergent quantity essentially, is a divergent quantity. The ladder diagrams like the ones which I shown you here, and the sum of all these things completely divergent, the rest will converge essentially, but this divergent part completely divergence. So this is a non-perturbative effect essentially, this is a non-perturbative. When you sum it over, it just becomes a divergent series and you do not know how to deal with this. So you deal with it in terms of some Bethe-Salpeter equations. You can write an equation which is, and you can also solve these equations by using some numerical methods or something. There are also equivalent class of equations called Dyson-Schingler, slightly different but equivalent class. But the only way which is much more interesting and reasonable, physically much more handleable, this Bethe-Salpeter and Dyson-Schingler need some numerical technique. You cannot solve them in most cases, essentially you cannot solve them exactly in most cases, you have to make some approximations or something. Okay. So the only way to solve them sometimes is numerically, sometimes by, then there are error prone and various things essentially. But there are techniques in which you can solve them by mapping these equations, by mapping this entire system, divergence system, into a non-relativistic system, essentially into a non-relativistic system. For example, you can map it into for example, one of these cases can be mapped into a Schrodinger equation times in particular interaction essentially. Okay. So this again, then Schrodinger equation is a non-relativistic system essentially, not Schrodinger equation. So this is what it happens essentially, these bound states like positronium or something, bound states are best dealt in non-relativistic manner essentially. Then you calculate relativistic corrections to it essentially, you calculate relativistic corrections to it. Okay. So that is what we will precisely do now essentially. We will start with the simplest case. Okay, there are this positronium, quarkonium and these bound states also contribute in higher order QED corrections or higher order QCD corrections also, if you have a very precise quantity which you are measuring essentially, some of these bound states also contribute. Quarkonia essentially, quarkonia in the QCD sense, in the strong interactions, all of them are treated in this particular fashion essentially, you start dealing them with the particular fashion. Okay. So but we will deal them in using non-relativistic quantum mechanics. So we will do this thing that we will map this entire problem into a non-relativistic thing and then compute higher order corrections to this essentially, relativistic corrections to this. So one of the most famous example is a well known example of relativistic corrections to hydrogen atom. Now how do you, but before that how do you write hydrogen atom potential in, how do you solve this relativistic correction in hydrogen atom starting from Dirac equation, starting with Dirac equation is a completely relativistic case essentially. To do that I will start with the so I will start with non-relativistic reduction of Dirac equation and then I will continue to do the thing essentially. So to start do the non-relativistic reduction of the Dirac equation, I will do the same thing like I did for non-relativistic reduction of similar to Klein-Gordon field. So I start with a wave function, assume a positive energy solution of the form psi of xt is equal to or RT or whatever, because RT makes sense because you want to write a hydrogen atom, then there are this radial, it is a radial solution and everything. So, let us write it in terms of RT essentially. Chi of R times eta of R whole into e power minus Et. Now E, what is E? Now here the way I wrote, m is the rest mass essentially, m is the rest mass. Okay. Now there is no concept in non-relativistic mechanics of rest mass essentially, because there is no rest mass and there is no relativistic mass essentially. So I want to make so E is equal to m plus the correction, which is like an energy essentially. The energy should be comparable to the mass essentially, the energy T should be smaller than the mass essentially. So the basic idea is that the momentum, if you want to convert it into, you are taking the large m limit. So you are taking the limit where the mass of the particle is has much larger, so it is almost like large m limit. So m will be much greater than T, which is nothing but mod P essentially, and if you add potentials, let me assume relativistic potentials, say V mu or A mu or whatever, okay, let us call it A mu say for example, because A mu is equal to A0 A bar, okay. So E times A mu, there is always a E or a, so all components m is greater than A0 mod A bar, there is an E factor there essentially. So m is the largest element in your equations essentially, m is the largest element in your equations. Now then you start put this solution large m limit. Now put this wave function in Dirac equation. Put this wave function in Dirac equation, and this gives me two equations, T chi is equal to A0 chi plus sigma dot P minus A eta, and the other one would be 2m plus T eta is equal to V0 eta plus sigma bar dot P bar minus A chi. Okay. Now you see that the lower components of the Dirac spinor, because you start with Dirac spinor which has both two components, right, essentially chi and eta. Now if you look at the second equation, the eta component is much smaller, the eta component is suppressed by the mass and thus is much smaller than the chi component. Okay. Because this is 1 by m T, forget, you can forget, it is always 1 by m, this is always be very small essentially. So you can put this eta solution in terms of sigma by P minus A by 2m back into the eta equation, back into the eta equation or the chi equation, sorry. So you can solve this, let me call it solve 2 in the large M limit and put it in 1. This gives me T chi is equal to A0 plus sigma P minus V P minus A sigma bar dot P minus A 1 by 2m plus T minus A0 sigma dot P minus A bar times chi. Okay, T minus A bar times chi. Okay. Now what we can do is we can estimate what is T, okay, from the lower order equation. So we can estimate what is T from the lower order equation. So T is roughly this, okay. So T is roughly this. A0 plus 1 by 2m sigma dot P minus A bar sigma dot P minus A. This is your non-relativistic reduction. You can write it explicitly in terms of this is nothing but your Schrodinger equation, okay. This is nothing but your Schrodinger equation written as this with a Pauli term. So you can take the sigma dot p, essentially this just becomes a double derivative essentially, okay. This just becomes a double derivative and this is 1 by del t and A0 is nothing but your the potential. You can take it as phi V phi order the scalar potential, and A bar can be your sigma dot b term, sigma dot p term, which is nothing but your Pauli term essentially with the Pauli terms, okay. So what we have derived is a non-relativistic reduction of the Schrodinger equation from the Dirac equation essentially in terms this is nothing but Schrodinger equation by identifying P bar is equal to del and putting appropriate H bars, okay. Wherever there is H bar you can put it back essentially. We took on H is equal to 1 but in non-relativistic quantum mechanics and everything. Now this so what we did was a transformation. We chose one particular okay, we chose one particular wave function and put it back into this, okay, put it back into this and okay, because m is large essentially we can neglect the other two and then we end up having this particular relation essentially. This is nothing but your Schrodinger equation, and like I told you this is nothing but your Schrodinger equation in terms of with the Pauli terms. Now, but this is not the best way to solve it essentially. This is not the best way to get the non-relativistic reduction of the what do you call of the Dirac equation of the Dirac. Now the problem is that it depends upon what T you are using. Okay, it depends upon what T you are using. So if you use a different T, it gives you a different answer essentially. It sort of T dependent quantity, which people we would say we shouldn't like. We want an M dependent, we want something of the order of P square by M essentially. We want something which mimics the non-relativistic case essentially. So which mimics non-relativistic case, and for that we need a further transformation, a different kind of transformation, which is called the Foldy-Wouthilson transformation. When I say better, means it is much more controllable, mathematically consistent, better and consistent transformation to the non-relativistic limit is called the Foldy Foldy-Wouthilson transformation. Okay. So now I will just write down this Foldy-Wouthilson transformation. Essentially we have to write it in particular fashion, and then let us see essentially. So let me write in down first the Dirac equation in a particular fashion in terms of the Dirac matrices. So let me write it down. To introduce the Foldy-Wouthilson transformation. Now this transformation is a transformation which takes the relativistic equation to a non-relativistic equations by a series of unitary transformations, unitary rotations essentially, by a series of unitary rotations. Okay. So that is the basic idea, that you should unitarily transform a relativistic system to a non-relativistic system rather than just arbitrarily choosing a particular wave function and deriving this thing. Okay, it gives you the correct thing, it gives you the Pauli equations, and this also confirms that okay, the moment you have the Pauli terms, you have the Pauli terms here essentially. So you have the Pauli terms here, where is it for the smaller. So these are, once you have these Pauli terms, okay, now you can say, oh, I have the Pauli terms, so that means that it is spin half particle, it is a non-relativistic, it gives me the Schrodinger equation with Pauli terms, so it means that it is a spin half. So it is magnetic moment is 2, so which is all consistent, this works. I am not saying this does not work, but this is this does not bring in all the features of 1 by m terms essentially, in the sense that it does not give you all the features of the 1 by m terms, and if you want to do a higher order correction, step by step order corrections, relativistic corrections to this system, this is not the best way essentially. So this is not the best way. So the best way is to actually have a transformation which is to use this Foldy-Wouthilson transformation starting from the relativistic system, and then use a series of these unitary transformations one by one and then get back this one essentially. So what does the Foddy-Wulfstone transformation look like? Essentially I will introduce you, and in the next class we will conclude it. Let me introduce you this thing. Chi eta is just a Dirac equation minus with a potential essentially m0 plus alpha times p minus a bar plus m beta bar chi eta is equal to h chi eta. Now these alpha matrices are the Dirac alpha beta matrices which we introduce in earlier course and in earlier lectures. Okay, which we introduced in the earlier lectures essentially. So the Foddy-Wulfstone transformation essentially is defined as a unitary transformation. Okay, transformation is defined as a development transformation. So unitary transformation U is equal to A beta plus lambda by m. So it has a 1 by m expression essentially 1 by m alpha dot p. Now it looks nice. Okay, it is A beta, okay, where this A I should not call it as A, let me call it A tilde, okay, A tilde beta times lambda times alpha dot p by m. So what you are expressing, this means that when you are making this transformation you are always making getting a 1 by m term essentially, where A tilde is equal to square root of 1 minus lambda square p square by m square essentially, and lambda is a parameter. You choose this parameter later on, say lambda is a parameter. Now this parameter, this u is unitary. It is very easy to see that u dagger is equal to 1. So it is a unitary matrix essentially. Okay. So what we want to do is we want to apply this transformation on the Dirac Hamiltonian written in that particular fashion in the presence of potential essentially. Okay. We want to apply this this transformation in the Hamiltonian in the presence of this u, okay, and this we claim that it gives you the correct what do you call as the non-relativistic limit or relativistic corrections to the non-relativistic limit of the Dirac equation. So this transformation takes you the Dirac equation to non-relativistic Dirac part plus with relativistic corrections essentially. Okay. So I will stop here, we will continue with this Foddy-Wulfstone transformation and then discuss about the corrections to the hydrogen atom relativistic spectrum in the last class of this lecture series essentially. Okay. Thank you very much. Okay, I will stop here. Thank you.